After a decade of delays, Dream Chaser just passed its final ground tests. Sierra Space confirmed the spacecraft completed electromagnetic checks, high-speed runway tests, and full landing rehearsals. But here's what makes it different. While Dragon capsules splash into the ocean with parachutes, Dream Chaser lands on a runway like an aircraft, bringing cargo back far more gently. Why does this matter? Delicate science experiments need stable conditions during re-entry, and runway landings provide exactly that. Let's dive right in. At Kennedy Space Center, engineers placed Dream Chaser inside a specialized electromagnetic test facility. Every spacecraft generates electrical noise from its own systems, and if that interference disrupts navigation or communications, the entire mission fails instantly. Dream Chaser had to prove all its computers and control systems could operate simultaneously without conflicts. What happens when systems interfere with each other in orbit? There's no ground control to fix it in real time. The spacecraft passed with flying colors, but the real challenge came next, the high-speed runway test. Engineers attached Dream Chaser to a heavy truck and pulled it across the runway at landing speeds, simulating the exact forces it will face after re-entering Earth's atmosphere. The landing gear absorbed the impact, brakes engaged smoothly, and the steering system held the spacecraft stable through deceleration. This wasn't just about proving it could touch down. Could Dream Chaser handle the transition from 17,500 miles per hour orbital velocity to a complete stop on a runway without human intervention? Here's where the design gets fascinating. Most modern spacecraft are capsules. Dragon and Starliner both use round capsule designs with heat shields and parachutes, splashing into the ocean where recovery ships must fish them out of salt water. That ocean exposure causes corrosion and wear, increasing refurbishment costs between flights. Dream Chaser takes a completely different approach. It launches vertically on a Vulcan Centaur rocket, but returns horizontally like an aircraft, landing on a runway with no parachutes required. No pilot controls the descent. The entire re-entry sequence runs on autonomous flight software. Why does this matter for cargo? Because parachute landings hit hard. When a capsule slams into water, the deceleration forces can reach several Gs, potentially damaging delicate experiments that spent months growing crystals in microgravity or testing new materials in space. Runway landings are far gentler, keeping sensitive cargo stable throughout the entire return journey. The current Dream Chaser configuration carries up to 5,000 kilograms of pressurized cargo inside its main body. It also attaches a disposable module called Shooting Star, which holds additional unpressurized cargo and provides power during the mission. When Dream Chaser returns to Earth, Shooting Star separates and burns up in the atmosphere, while the main space plane survives and lands for reuse. But there's another advantage capsules can't offer: immediate cargo access. When Dragon splashes down, recovery crews need hours to locate the capsule, secure it, lift it onto ships, and transport it to shore. Only then can scientists access their experiments. Dream Chaser rolls into a hangar within minutes of landing. For time-sensitive biological samples or materials that degrade quickly after leaving microgravity, those hours make the difference between success and failure. How many experiments have been compromised by extended recovery times? Dream Chaser uses a lifting body design, meaning its shape itself generates lift during re-entry, rather than relying on large wings. This concept traces back to NASA research from the 1960s and 70s, when engineers tested experimental lifting body aircraft to understand how spacecraft could glide safely through the atmosphere. Those studies influenced the Space Shuttle and other programs. In the 1990s, NASA designed a concept called the HL-20, which became the foundation for Dream Chaser. Sierra Nevada Corporation acquired the project and developed it into a real orbital vehicle using modern composite materials and advanced flight software. But Dream Chaser's path to space wasn't smooth. Originally, it was designed to carry astronauts. When NASA launched the Commercial Crew Program after retiring the Space Shuttle, 3 companies competed. SpaceX offered Dragon, Boeing offered Starliner, and Sierra Space offered Dream Chaser as a reusable spaceplane. Many believed Dream Chaser would be a strong competitor. What went wrong? Funding changes, redesigns, and repeated delays slowed development. SpaceX pushed Dragon forward rapidly, while Dream Chaser struggled to keep pace. NASA eventually selected SpaceX and Boeing for crew transport, moving Dream Chaser into a cargo-only role. SpaceX flew Dragon's first uncrewed test to the International Space Station in 2019. By 2020, it was carrying astronauts. Since then, Dragon has flown dozens of missions with a strong safety record, becoming NASA's primary crew transport vehicle. Boeing's story went the opposite direction. NASA actually awarded Boeing more money than SpaceX because of Boeing's history with Apollo, the Space Shuttle, and the ISS. Boeing seemed like the safer bet, but despite larger funding, Starliner quickly fell behind. In 2019, its first uncrewed test failed after a software timing error caused the spacecraft to burn too much fuel. It couldn't reach the ISS and had to return early. NASA later discovered a second critical software fault that could have caused a collision during separation, potentially destroying the vehicle. These failures exposed serious testing and quality control problems inside Boeing. The company had to repeat the uncrewed test at its own expense. The second attempt in 2022 finally docked with the ISS, but suffered thruster failures and propulsion system issues. Several maneuvering thrusters shut down in orbit. Engineers traced the problem to faulty valves and moisture-related corrosion in the propulsion system. Can you trust a spacecraft that can't control its thrusters? In 2024, Starliner finally flew its first crewed test with 2 astronauts aboard. The capsule reached the ISS successfully, but after docking, helium leaks and additional thruster failures appeared in the propulsion system. These problems made it unsafe for Starliner to perform the deorbit burn needed to bring the astronauts home. NASA made a critical decision. The astronauts stayed aboard the space station for months while Starliner returned to Earth empty because it couldn't be trusted for safe human re-entry. The astronauts came home on Dragon instead. NASA then canceled Starliner's upcoming crewed missions indefinitely. By this point, SpaceX had completed numerous successful crew flights at lower cost with far fewer problems. Boeing, despite receiving the larger share of funding, delivered repeated delays, failures, and safety concerns. This is the landscape Dream Chaser enters. Unlike SpaceX and Boeing, Dream Chaser isn't trying to replace crew capsules right now. Its focus is cargo transport, delivering supplies to orbit and bringing experiments back with that crucial gentle runway landing. Dream Chaser is also fully reusable. After landing, it can be inspected, refueled, and prepared for another mission. Over time, this could significantly lower the cost per flight if refurbishment proves easier than capsule recovery and rebuilding. Sierra Space believes the spaceplane can fly many missions over its lifetime instead of being used once or twice. The first mission will be a demonstration flight launching in 2026. Interestingly, it won't dock with the ISS during this initial flight, even though earlier plans indicated it would. Why the change? The mission will focus on proving orbital flight and runway landing capability. Once that flight succeeds, future missions will support full NASA cargo deliveries. This first orbital attempt represents the most critical moment in Dream Chaser's decade-long history. Until it flies, everything remains theoretical. Heat protection during re-entry, real-world system performance, and autonomous landing can only be proven once the spacecraft completes the full round trip from Earth to orbit and back. After 10 years of development, Dream Chaser stands ready to prove what many thought impossible, that a spaceplane can deliver cargo more effectively than traditional capsules. While SpaceX's Dragon dominates with proven reliability and Boeing's Starliner struggles with safety failures, Dream Chaser offers something neither can match: the ability to protect delicate experiments from the violent forces of ocean's splashdowns. The 2026 demonstration flight will answer the ultimate question. Can Dream Chaser survive the scorching heat of re-entry and execute a perfect autonomous runway landing? If it succeeds, Sierra Space opens a new chapter in cargo transport, one where biotechnology experiments, crystal growth studies, and medical research return to Earth intact instead of damaged by parachute impacts and saltwater exposure. If it fails, a decade of work ends on a California runway. But here's what makes this moment different from Boeing's struggles. Dream Chaser already completed every ground test. The electromagnetic systems work. The landing gear handles real forces. The autonomous flight software functions flawlessly. Unlike Starliner's software errors and thruster failures discovered mid-mission, Dream Chaser validated its systems before launch. The spacecraft doesn't need to prove it can fly. It needs to prove it can survive space. For researchers waiting years to retrieve their experiments, those gentle runway landings could mean everything. The difference between breakthrough discoveries and destroyed samples often comes down to how cargo returns home. Will Dream Chaser deliver on that promise? We'll find out in 2026.